Okay, what are the different number systems is decimal with base 10. You can convert from binary to decimal and from decimal to binary. In multiplication, there will be intermediate products. Like in our decimal system, answer will be 111 to the base 2. Hello students, welcome to the session of Digital Electronics. I am Dr. Saumeshri from Department of Computer Science, Vidhyaashram College. Till now, I just finished the concepts of first unit. Okay. Now, in this session, let us have a quick review of or revision of the first unit. What are the things that we have learned in this unit? The first thing that we have learned in all these sessions is the number system. Okay, the number system. Okay, what are the different number systems is decimal with base 10, octal with base 8, hexadecimal with base 16 and binary with base 2. Okay, we know about different number systems. You can revisit the sessions to know about all these things in detail. Okay, after getting into a number system, we know about how to represent the numbers in number system, different number systems. Like for decimal system, if it is 101, we can represent it as 1 into 10 to the power of 2 plus 0 into 10 to the power of 1 plus 1 into 10 to the power of 0 in decimal. When it is octal, it will be same 101 can be represented as 1 into 8 to the power of 2 plus 0 into 8 to the power of 1 plus 1 into 8 to the power of 0. Same 101 can be represented in hexadecimal as 1 into 16 to the power of 2 plus 0 into 16 to the power of 1 plus 1 into 16 to the power of 0. Is it not? If it is binary, it can be representing as 1 into 2 to the power of 2 plus 0 into 2 to the power of 2 plus 1 into, it is 2 to the power of 1, 1 into 2 to the power of 0. Same number can be represented in different system like this: 10, 8, 16 and 2, base 2. Okay, you can represent the numbers like this. Once we know about number system, this is the tabular representation of the different system. Basic 0 to 9, decimal, binary is 0, 1, octal is 0 to 7, hexadecimal is 0 to 9 and A, B, C, D, E, F. Okay, these are the number systems that we have studied. Once we know about the number system, next is to know about how to convert the number from one system to another. Okay, so we have different number systems. You can convert any number in any system to any other system. Okay, how do you convert is, if it is integer part, will be following the successive division. As you know, division. If it is a fractional part, you can have the successive multiplication of the numbers, multiplying with particular base, okay, dividing with the particular base and considering the quotient and the remainder. Quotient will be next input, remainder will be taken for the conversion data. How we can convert the numbers is, you can convert from binary to decimal and from decimal to binary, binary to octal and octal to binary, binary to hexadecimal and hexadecimal to binary. Along with that, you can convert from octal to decimal and decimal to octal, hexadecimal to decimal and decimal to hexadecimal. Is it not? So, these are the some of the conversion operations that can be done on the different numbers. Is it not? How do you convert binary to decimal is multiplying. If you have 1101, how do you convert binary to decimal? 1 into multiply with the base 1 into 2 to the power of 3, 1 into 2 to the power of 2 plus 0 into 2 to the power of 1 plus 1 into 2 to the power of 0. Is it not? So, it will make 8 plus 4 plus 1. So, 13. Is it not? How do you convert this 13 to binary is divide it by 2. 1, remainder is 0, remainder is 1, remainder is 1. So, it is a 1101 with base 2, this is with base 10. Okay. So, this is how you can convert from binary to decimal and from decimal to binary. Okay. Next is binary to octal. How do you convert binary to octal is 11000101. How do you convert is making it group of 3 digits. Is it not? So, 3 digits will make 001 is all about 1, 100 is 4 and 101 is 5. 145 with the base 8. How do you convert the number from octal to binaries? Suppose if I take 246, how do you convert? 2 will be represented as 010, 4 can be represented as 100, 6 can be represented as 110. Okay. So, this is base 2, this is base 8, 8 to 2, this is from binary to octal, this is from octal to binary. Okay. Next is the binary to hexadecimal. How do you convert the data from or number from binary to hexadecimal is making it group of 4, isn't it? So, 1100, 1101. How do you convert? First make the group of 4 digits, fill it with 00. Okay. So, this is of base 2. How do you convert it to hexadecimal? 0011 represents 3, 0010 represents 2, whereas 1101 represents 13, like 1 into, this is 8, 2 to the power of 3, 2 to the power of 2 and 2 to the power of 0. 8 plus 4 plus 1 represents 13. Cannot express 13 in hexadecimal. How do you represent 13 is using A, B, C, D, E, F. Okay. 13 will be D, isn't it? So 32D will be with the base 16. Okay. 13 will be D. How do you convert to hexadecimal to binary is, suppose if I take 65B with the base 16 to binary is, 6 can be represented as 0, 1, 1, 0. 5 can be represented as 0, 1, 0, 1. Okay. B can be represented as, B represents 11. 11 can be represented as 1, 0, 1, 1. Okay. With the base 2. Is it not? 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1. Okay. With the base 2 will be used to represent the hexadecimal number in binary. Next comes is octal to decimal. Okay. How do you convert a number from octal to decimal is, suppose if you have 432 with base 8, how do you convert it to decimal is 4 into 8 to the power of 3, 8 to the power of 2 plus 3 into 8 to the power of 1 plus 2 into 8 to the power of 0. Okay. Result will be 256 plus 24 plus 2 will be, okay. So, in the number system 10, base will be 10. Okay. This is how you can represent an octal number, or you can convert an octal number into decimal. How do you convert decimal to octal is, if you have 84, how do you represent that in octal is, 84 will be divided by 8. Okay. So 0, remainder is 1. Can represent it as 1, 2, 4 with the base 8. 84 in octal can be represented as 1, 2, 4. Alright. So this is about octal to decimal, decimal to octal. Next is, how do you convert hexadecimal to decimal and decimal to hexadecimal? If you have hexadecimal, say 35C 16, how do you represent? 3 into 16 to the power of 2 plus 5 into 16 to the power of 1 plus, it will be 12 into 16 to the power of 0. Okay. So, this will be 768 plus 80 plus 12. Okay. It will be 860 to the base 10. How do you convert decimal to hexadecimal is, suppose if you take 93, so you can divide it by 16. So the number 93 in decimal can be represented as 93 with the base 10 can be converted to hexadecimal using 5, 5D with base 16. Okay, 5D with base 16. This is how you can convert a number from hexadecimal to decimal and from decimal to hexadecimal. Okay, so next, after knowing about the number conversion, next is how to carry the binary arithmetic in binary numbers. Okay, so you can have addition of numbers, subtraction of numbers, multiplication of numbers and division of numbers. In addition, you have to take care of the carry. In subtraction, you have to take care of the borrow. In multiplication, there will be intermediate products like in our decimal system product. There will be intermediate products in the multiplication. And division is as usual in decimal system. How do you perform in decimal system? Okay. So you have 4 types of arithmetic operations that can be carried out on binary numbers. This is how the computers are going to process your arithmetic operations in decimal system. Okay. After this, next is to know about complement system. How do you perform the complement in R's complement? Generate the complement in R with base R. There will be tens complement and 2's complement. When we have R minus 1 complement, in this we have 9 complement and 1 complement. 9's complement and 1's complement. Here we have 10's complement and 2's complement. Okay. You know about the methods how to create the complement. Okay. In R's complement, convert it to, if it is 10's complement, subtract the first LSB from 10 remaining from 9. Suppose if you have the number 4812, how do you generate the 10's complement is subtract first LSB from 10 will be 8 and subsequent numbers from 9. It will be 8, 1, 5. 5, 1, 8, 8 will be the 10's complement. Okay. What about 2's complement? When you have 1, 0, 1, 1, 0, how do you generate the 2's complement is leave the LSB zeros as it is, leave the first non-zero value as it is, change the remaining values from 1 to 0 and 0 to 1. Okay. So, once 2's complement, it will be 0, 1, 0, 1, 0. Okay. So, this is R's complement. When it comes to R minus 1's complement, how do you generate 9's complement is same value 4812. How do you generate 9's complement is subtract all the digits from 9. It will be 5, 1, 8, 7. Okay. In case of one's binary number, same 10110, you have to interchange all the ones and the zeros. This will be, one's complement will be 0, 1, 0, 0, 1. Okay. So, this is about the r's complement and the r minus 1's complement. Once you know about the complement system, next is to know about subtraction in the complement system. How do you subtract two values in the system? Okay. So, complement system in r's complement or r minus 1 complement. You have to find out the r's complement, then add it. If there is any end carry, discard it. If an end carry does not occur, perform the r's complement. So, if you look at the example, if you take 1 0 1 1 1 0, subtract 1 1 0 0 from 1 0 1 1 0, what you have to perform is, if it is r's complement, you have to find out the 2's complement of 1 1 0 0. It will be 2's complement will be 0 1 0 0 0 1 0 0. Add this to the value 0 1 0 0. The result will be 0 1 1 1 0 1 1 0 1 1. Okay. So, you have to perform the r's complement because there is no carry. So, you have to perform the r's complement. This will be 0 0 1 1 1 0. Final result will be 0 0 1 1 1 0 or simply 1 1 1 0. Okay, this is about r's complement subtraction. Okay. When you have r minus 1 complement, you have to perform the same thing, but when n carry occurs, you have to add 1 to the LSB. So, example, if you take subtract 10101 from 10111 what you have to do is, first you have to find out the 1's complement of this. This will be 01010. Add this to the m. So, it will be 01010. So, there will be 0 110 110 1 1. If there is no end carry again, so take the r minus 1's complement. It will be 0 0 0 1 1 1 or simply you can take it as 1 1 1 to the base 2. Answer will be 1 1 1 to the base 2. Okay. If there is no end carry. If there is an end carry, you have to add this to the LSB. Okay. If you take another example, so first you have to find out the 1's complement of this. This will be 10 10. Add 11001. Then 1010 will be 110 110 110. There will be a carry of 1. Add this to here, this MS to this LSB, 110 110 100. That means answer is 100 with a negative sign. Alright. So, this is about subtraction using the complement system. Next comes is the weighted number system and the BCD. So, weighted number codes are which have a weightage to each of the position in the number. Okay. So, it represents a specific weight. Okay. There are certain codes that are used to express these decimal digits. Usually, there will be weighted number system. Only category that is available with the binary numbers with weight will be the BCD, that is binary coded decimal. where we can use 00 to 1001. That means up to 9, 0 to 9, 4 digits will be used, okay, with a binary code which are represented using 8421. Okay, so this will be from 0000 to 1001. Okay, so 0 to 9 are the BCD numbers. Okay, 4-bit binary number will be used to represent the numbers in BCD. Okay, there is an operation of addition in BCD numbers. How do you perform is, you have to add the numbers. If the result exceeds the decimal 9, you have to add a decimal 6 or binary 0110 to the value. If you take the example, if you want to add 1001 and 0110. So if you add this will become 1111, which is not a valid BCD number. For this, you have to add 0110. Okay, so this will become 1 0 1 0 1. This 1 will be discarded. So 0101 will be a valid BCD number. All right. Next is about non-weighted number system. In non-weighted number system, we have there is no weightage for the position. Okay. In this, we have 3 codes, that is XS3 and the gray codes. Okay. XS3 code is adding extra 3 to the normal decimal number or normal BCD number. Rather, it is called as adding extra 3, decimal 3 or 0011 to the BCD number. Alright. It is derived from 8421 by adding 0011 to the each word of BCD or each code of BCD. Alright. Next comes is another non-weighted code, that is gray code, where only 1 bit will change each time. There is no fixed change in the gray code. It changes dynamically. What changes is 1 bit will change with the increment of each decimal number. If you go from 1 to 2, there will be a change of 1 bit. Which bit? We don't know. It will be dynamic. Okay. If it from 2 to 3 or 3 to 4 each time decimal number increments, there will be change of only 1 bit in the number in a gray code. Next we have parity bits, generating odd parity and even parity. Next is the alphanumeric codes. What is the alphanumeric codes are? That represents the numbers, alphabets as well as the characters or the symbols. Okay. In alphanumeric codes, we have ASCII, American Standard Code for Information Interchange, Extended Binary Coded Decimal Interchange Code. Again, this is a way of representing the numbers, characters and the alphabets. Then a 5-bit, group of 5-bit barcode code. Okay. So this is how you can represent, can use any of these methods to represent the alphanumeric characters. The most widely used representation is the ASCII code. The next thing is to know about fixed and floating point numbers. How do you use fixed and floating point numbers is, so this representation has fixed number of bits. only this much will be accommodated. More than that will be discarded. Like if you have 555.6.512301 and the limit is only for 4 digits or 5 digits fixed. Suppose we have this. If it is 5 digits, the digit will be discarded, extra digit will be discarded because the number of bits will be reserved in a fixed number system. Okay? It will be rounded off, or it will be extra bit will be discarded, or extra bit will be rounded off to the next value or previous value. But only fixed number of bits are reserved for integer part as well as for the fractional part. Okay. There will be 3 parts in fixed point number. One will be for 1 bit will be for representing the sign. Next will be integer field. Next will be fractional field. Okay. Next is floating point numbers. So this representation does not reserve any kind of bits. However, you can use the numbers, like you can have the numbers like this. 101.382461. You can use the numbers like this. There is no fixed bits for the integer part or the fractional part in floating point number. Instead, it reserves a certain number of bits for the number called mantissa or significant. There will be extra bits for mantissa or significant and a certain number of bits to decimal places. So, there will be 3 parts again in floating point, but this time in floating point 1 bit again will be for signed bit in case of signed numbers. Next will be the number or decimal place. One part will be for decimal and last will be for mantissa. Okay. There is no fixed number of bits in the floating point numbers. Okay. There will be 3 parts: sign, decimal and the mantissa part. Okay. Sometimes in the memory place, the fixed point will be useful because it reduces the more usage of the memory in the computer. In such a case, fixed number representation is better. When you take the calculation purpose, even some of the fractional points may be important, may be critical. Suppose if you take the example of rocket launching, in such case of for scientific calculations, even minute points will be important in case of such incidents. In such a case, it has to take care of each of the digit in a number. That means you cannot discard or round off any value. You have to take fractional part, how much digits may have, bits may have. We have to consider all those things for the calculation. In such a purpose, in such an application, floating point numbers are more useful. Okay. This is where you can have the application of fixed point, fixed location, fixed representation as well as floating representation, each of which will have their own application in the digital devices. Alright, this is all about the concepts that are given in the first unit. Okay, thank you.